After Alin and Fokyeon, thank you for giving me the opportunity to tell you the story about ideas I've learned over the past 7 or 8 years. This is based on joint works with a variety of authors. In particular, my view on this topic has been shaped in the past 4 years or so, theoretically by the collaboration with Mahmoud Abu Khamis and Dan Suchiu, any one of whom could have given the same talk, and also by colleagues in practice at LogicBox and Relational AI. It is very nice to be able to see your algorithm, being actually implemented and inside of an engine, and the in and out of where it works and where it doesn't work. It's very fulfilling. So, for those of you who are doing just pure theory, implement them, and I think you'll gain a lot more insight. There's actually a paper with exactly the same title on arXiv and also the proceedings. So I will try not to tell you the things that you can actually read from the paper. So in particular, there's a rich history of ideas from a variety of areas on this problem. You can just read from the papers, and there's a list of like 7 to 80 papers, references in the paper. I will try to define the problem and then give you an example, give you a hint, and hopefully that will raise your interest in going, studying more about these ideas. All right, so in the past 10, 15 years or so, there have been 3 fundamental, some exciting progress in 3 fundamental problems in relational data management systems. So the first one is on query plans. This is not what this talk is about. Basically, the new ideas involve query plans that are based on variable elimination or equivalently tree decompositions, and they can answer a very general class of queries from Boolean aggregation, max-min, CSPs, graphical model inference, and so on. So those are the references that you can go if you want to dig deeper into this topic. The second topic is bounding the output size of an intermediate result of a query, or the final output size of a joint query. And the third topic is on worst-case optimal join algorithms. And these are the 2 items that I would like to tell you more about today. Okay, so I have only one notation slide. Hopefully, bear with me. So I'm going to use 1 sub e to denote the indicator variable that's set to be 1 if the event is true and 0 otherwise. In particular, I will write 1 RAB to be 1 if the tuple AB is in the relation R, and 0 if AB is not in R, given that R has 2 attributes. We will be working with an input query hypergraph, and there will be a query which is the join of all of the input relations. There's 1 per hyper edge of the hypergraph, and the vertices of the hypergraph are exactly the variables occurring in the query, and R sub f is a relation whose attributes are, whose variables are indexed by f. So here's one example, the triangle query example. So here we have 3 relations, RAB, SBC, and TAC. So then the hypergraph is just a triangle graph. It's a very simple graph. But there's actually quite a few things you can say about this particular example already. And the second thing I want to get across is the notion of degree constraints. And it goes something like this. So if you look at this relation RABC on 3 attributes, RA, B, and C, then if you stare at it for a moment, you will notice that B and C functionally determine A. And I gave the same talk at AMW 2 weeks ago when I screwed up this example. But I think this is fixed now. And AMW was a wonderful event. This is a big shout out to the organizers of the conference, of the workshop. It's very nice. So you should go if you have a chance. Okay, so coming back to this relation, given B and C, you will know A because there's a functional dependency. Like B and C form a key of this relation. the way to write this as a degree constraint, it says that the degree of A given BC is at most 1, right? So when you have a degree bound of 1, then that denotes a functional dependency. Similarly, if you know A, then the number of different B's is at most 2. Okay? And I have this color-coded, so hopefully you can see that given A, number of different B's is at most 2. So this is called the degree constraint. Now the cardinality constraints, so this relation has something like 8 tuples. All that means is that condition on nothing, the number of different ABCs is at most 8. Okay? So in general, the degree constraint is nothing but a triple x, y, and an integer, where x is a set of variables, y is a superset of variables, and then given x, the number of different y's is at most n y given x. And you can read that off from a relational expression, but I hope it's clear from just looking at the picture. And the notion of degree constraints generalize both cardinality bounds and functional dependencies. Okay? So we'll be working with conjunctive queries given degree constraints. Okay, so given the input like that, there are 2 problems, right? So given a full conjunctive query such as the triangle query and a bunch of degree constraints, the first problem is what is the worst case output size for this query? So capital D is a database that satisfies all of the degree constraints, and we would like to find out what's the maximum output size bound for this query. And the second problem is that once we have determined the output size bound, can we design an algorithm whose runtime is determined by the input size, which is D, plus the worst case output size bound, and subject to a polylog factor, a polynomial in the query complexity, and also a log factor in data complexity. Okay? So an algorithm, if it satisfies this property, it's going to be called a worst case optimal join algorithm. And I inserted this thing just right before giving this talk in anticipation of Marshall's question of what is the thing that I hid behind the theory O notation. So I didn't hide any doubly exponential factor in query complexity in here. Okay? Yeah. All right. So there's actually quite a rich history of just trying to bound the output size. I'm not going to read this to you. From geometry to extreme combinatorics to constraint satisfaction to databases. But the thing I want to point out to you is that there are 2 fundamental arguments that were used. So one is based on the Holder argument that was based on a geometric inequality, and the other one is the entropy argument. And the story I would like to tell is that from these 2 ideas, then we can both use them to bound the output size and also to design the algorithms whose, the worst case optimal join algorithms, whose runtime matches the output size. So I have 4 things to tell you how to use these 2 arguments to prove the bounds and then to design the corresponding algorithms. The connection to geometry, to isoperimetric inequalities can be shown basically by this picture. In case you haven't thought about this idea before, a join problem is basically a geometric problem where in a triangle query you want to find the red points whose projections on the the AC plane is covered by the T relation, projected on the AB plane is covered by the R relation, and so on. So it's highly geometric, and if you generalize this idea from the discrete measure to the continuous measure, you will get the volume of a convex body in 3D space and so on. Okay, so that's the geometric connection in case you are curious. Now, in terms of algorithms, then there's also quite an interesting history. And in particular, one thing that was fascinating was that Todd, who was at LogicBox, designed and implemented this algorithm without knowing that his algorithm was actually worst case optimal. And then he only found out after we kind of dig this out and proved that the thing was worst case optimal. So not to be outdone, he came back and look at his algorithm and finally proved that it's also worst case optimal. However, the first set of results were only on the simple degree constraints, namely that they are only cardinality constraints. There was no worst case optimality algorithm on functional dependencies or degree constraints. And then later on with Mahmoud and Dan Suchiu, we worked on the more general degree constraints, and we came up with an algorithm called Panda, which is worst-case optimal in some cases, but not in some other cases. So it's not exactly worst-case optimal join algorithms. But the constraints are a lot more general, and they were also designed for a much larger class of queries called the disjunctive data log queries. Okay, so here are some takeaways in case, Marcelo raises up, you have 5 minutes left. This is the story I want to tell. So the key insight that we have learned over the past 7-8 years or so is that it turns out that you can turn a proof into an algorithm, and different proof strategies give you different algorithms. This is like one of the most elegant things that I learned from working on these problems. And the analysis of these algorithms and the bounds are also crucially based on linear programming duality. So you got to learn a little bit of geometry, but from a different angle. And there's a really deep and interesting connection to information theory and group theory, which I will not have time to tell you about, of course. They are really practical. So I'm very lucky to be part of 2 companies that have this class of algorithms implemented as inside of the core engine. So they are not just toy examples, they actually work in practice. And there are many open problems. So I listed something like 8 different open problems in the write-up that I have in proceedings. Please check it out. Okay. All right, so I'll give you a hint of what these, how you prove a bound and how you design an algorithm from proving the bound. And the idea is obviously if you can prove things for 3 and then let 3 go to infinity, then you get the general algorithm out. Okay. Of course, it took us about 2 years to actually push 3 to infinity, but that's a different story. Okay, so let's look at the triangle example. So here I'm going to look at a very simple set of constraints. Those are cardinality constraints. So suppose that we are given the triangle query joining 3 relations such that the size of R is bounded by NR, size of S is bounded by NS, size of T is bounded by NT. And the question is, what is the maximum output size bound? Okay? Now, if you put this query into any relational database management system typical of there, like Postgres or something, and you input this instance, you will see that any of the join query plan is going to have an intermediate result that is bounded by, that's going to be at least n squared. Okay? So any intermediate result is going to be at least n squared. Yet the output size bound, I'll show you later, to be only n to the 1.5. Okay? So somehow these join plans overcompute things, right? The main story is that if you join only 2 things together, you may be losing information. The worst case optimal join algorithms are supposed to join many, many things together. The more you join, the better, because the more you join, the more constraints there are, so you can actually filter out more things. Right? So that's sort of the intuition. But how do we prove such a bound? That the output size is bounded by n to the 1.5, right? So here's the first proof, the Holder argument. It goes like this. So we have the triangle query. So I can write the output size as a sum of a product. Okay? The sum is over all possible values of A, all possible values of B, all possible values of C. And we'll only have a 1 if AB is in R, and BC is in S, and AC is in T. So obviously, we only count 1 if the triple ABC belongs to the output, right? So this is sort of by definition, it jumps out like this. Okay? So the trick that I have used in the past 6-7 years or so is just to push the sum inside of a product. It's a very simple trick, right? So obviously, the 1RAB does not have anything to do with C, so we factor it out of the sum. So that's kind of trivial, right? But the inner sum, what we can do is we use Cauchy-Schwarz to bound the inner sum by the product of the square roots of the sum. Okay, so Cauchy-Schwarz says that the dot product of 2 vectors is less than the square root of the length of the 2 vectors. Okay. And so we apply this trick. So here, notice something kind of interesting. This is an equality that, the sum over C of one SBC, I hope I can point. There we go. The sum over C of one SBC is exactly the selection on S of tuples whose B value is little b. Right, so I'm just rewriting that expression, nothing more. The same with this here. Okay. So once you have seen this trick, then you can complete the next two steps of the analysis of the bound very simply by rearranging, pushing the sum over B inside and factor things that do not have anything to do with B outside. Apply Cauchy-Schwarz again. Then voila, you get the square root of R, S, and T. So, basically, if I told you this first trick, then you would have gotten the bound out immediately from this. Okay? So that's how you prove a bound using the Hölder argument. Okay? Now, how do we turn the proof of this into an algorithm? So all you have to do is copy the proof, and then you stare at the proof for a long time, and you realize that the proof is actually doing something like an algorithm. It's basically iterating over A, and then iterating over B, and then iterating over C. Right? So that's the algorithm. So it's going to iterate over A, which is in the intersection of R and T, but you project them down to A. Basically, you look for all possible bindings in A that makes sense, right? And then condition on that, you look for all possible bindings of B that make sense. Here now, is over R and S because only R and S share the attribute B. And finally, you loop over C. Okay, so this is a nested for loop. It's very different from the nested join that you probably are more familiar with. And then you report ABC because now ABC aligned with all three relations. Okay. Now the analysis is also kind of jumps out of the algorithm. So the inner loop is basically an intersection, right? So we are intersecting two sets. And the time it takes to intersect two sets is the minimum of the two sets sizes, of course, because you can always loop through the smaller of the two sets and look up in the bigger one, right? So it's going to be bounded by the minimum of the two sets. The minimum is bounded by the geometric mean, which is the square root of the product, and then it's basically comes out to be that expression. Okay, so this whole thing is just says that we can intersect two sets in the time it takes to iterate over the smaller of the two sets. That's very simple. Now the outer loop, you see that we only get into the inner loop for all of the bindings that align with R. So all we have to do is to sum over A and B. And then these are the bindings that align with R. If they don't align, then we don't multiply in this factor. So this indicator variable occurs there. But then you look back at the proof. This is precisely that expression, right? So precisely the same expression. So then you let the proof run the rest of the analysis. You don't have to do anything else. So stare at the algorithm and let the proof run the analysis for you. And that is basically the proof that the algorithm runs in time square root of R, S, and T. Okay, so now this is the second proof and then the second algorithm. The second proof is not based on Hölder inequality, it's based on entropy view of things. So suppose we have three relations R, S, and T and whose join is this, right? And then Shearer came up with this idea, which is a wonderful idea that you can use in many different contexts. We tried to use this in a back semantic with Phocion, but it didn't quite work out yet. Okay, so what we do is we will select from the output size, from the output of this query, a uniform distribution over three variables, A, B, and C. So let's select triples A, B, and C uniformly from this distribution. Now, one thing we know about entropy is that the entropy of the uniform distribution is exactly the log of the support of the distribution. So this is an equality, right? Okay. So then the joint distribution actually imposes marginal distribution on AC, on BC, and on AB. But if you look at the entropy, the marginal entropy, this is not going to be necessarily uniform anymore. In this case, this is certainly not uniform, right? So it is upper bounded by the uniform distribution, by the entropy of the uniform distribution. Okay? This is a fundamental, basically it follows from Jensen inequality. Okay? So it basically says that HABC is bounded by log of 4. HAC is bounded by log of 4 in this case. Similarly, HBC is bounded by log of the number of tuples in S, and also HAB is bounded by log of the number of tuples in R. Okay? And furthermore, what we can say even more is that H of B given A is bounded by log base 2 of 3 because for any given A, there are at most 3 values of B. Just by looking at the statistics from relation R, you can derive bounds of that form. Okay? So all of the things that we can read off from the statistics of input relations become constraints that we can input into the algorithm and into the bound. And those are the degree constraints. Now, in particular, this function satisfies the following property. The function h is entropic. What it means is that it's an entropy. Right? And then it satisfies all of those degree constraints. Okay? So we have been able to relate the output size bound, the output size, to some function of which is entropic and which satisfies some degree constraints. So we turn this into a bound. So the bound goes like this. Because it was equal to h, and h is entropic, and it satisfies degree constraints, so it's certainly less than or equal to the maximum over all functions which are entropic and satisfy degree constraints. Okay? So those are the degree constraints that h is satisfied, and we use this to prove yet another bound. And this will be a little bit of magic. It took a while to figure this out. So it goes something like this. We have 3 terms, HAB, HBC, and HAC. Let's say this is an entropic function. So the first thing we do is we use the conditional entropy formula that says that HAB is equal to HA plus H of B given A. This is the chain rule of entropy. Okay? Or the same as the chain rule of probability. This is exactly the definition of conditional entropy. And then we rearrange things. So A goes with HBC, and then HB given A goes with HAC. Now the next thing, which is super important in entropy inequalities, is called the submodularity rule. What it says is that if I condition on more, my entropy is going to be reduced. Okay? Because the more I know, the less uncertain I will be about the distribution. So that's all there is to submodularity. So H of A is certainly more than H of A given BC. And similarly, H of B given A is certainly more than H of B given A and C together, right? Because we are gaining knowledge now. So these rules are called the submodularity rules. But the nice thing is that now I can compose those two, right? Using the conditional entropy rule again, the chain rule again, to get back HABC and HABC. Okay? So overall, what this shows is that 2 times HABC is smaller than HAB plus HBC plus HAC, as long as H is an entropy. So we use this to prove a bound that says, okay, log of Q, which is less than max of HABC, right? HABC, I just proved to you over here, is less than the average of the sum. Now we apply the degree constraints. Log, H of AB is less than log R, HBC is log S, and HAC is log T. So you sum over the 3 logs, which is the log of the product. And voila, again, it's square root of R, S, and T. Okay? This is a very different proof from the previous proof. It's a little bit magical. There's this step that how do we know how to decompose things so that, somehow they kind of realign again, all the stars align. But the beauty of this proof, assuming somehow you know how to do that, is that you can again copy the proof and then now interpret every step of the proof as an algorithmic step. Okay? So in this case, I just copied the proof from the previous page. I didn't, cheat you and added some terms in here. So now you would think of the starting points as R, S, and T, right? So the first step was to do this conditional entropy rewriting, right? So then I will interpret this as partitioning R into two parts, the heavy part and the light part. This is like dealing with skew in a database. Okay? And the heavy part is defined to be the set of tuples whose degree is more than a certain threshold, and the light part is a set of tuples whose A degree is less than a certain threshold. I'll tell you what the threshold is later. It's just something that's very heavy and something that's very light. Okay? And then we just have to follow this. You chase this through. And what this says is that let's join the heavy with S and join the light with T. Okay? And that's exactly what the query plan is going to be. And then you get the output, which is the heavy part of R joined with S and light part of R joined with T. And then the output is going to be the union of those two. And it turns out that if you set the threshold correctly, then the output size is, both of the intermediate output sizes are also bounded by square root of R, S, and T. Okay? This is a very different query plan compared to the previous one, but things work out to be precisely the same. How much time do I have? Okay, awesome. Yep. So I have accomplished the goal of telling you two proofs and two algorithms based on two different ideas. So now let's actually talk about the current landscape and some open problems. Okay, so there are lots of open problems. I can't, I don't have time to tell you about all of them. But basically, if you generalize the entropy argument to a general query, with general hypergraphs, they don't have to be the triangle query anymore. Then you would end up with something like called the entropic bound, where you have to, optimize over a function which is supposed to be entropic and satisfy the degree constraints. In fact, even this equality is actually not obvious, okay? But we can prove that this is an equality. The problem with entropic functions is that they form a cone which is not topologically closed and not polyhedral. The problem of determining if a function is entropic is not known to be decidable. So this is a big open problem for complexity theorists in the audience. This is kind of also a big open problem in information theory too. Deciding whether a given vector is an entropic vector or not. Okay? So because of this, what we have to do is we have to relax the problem gradually. So the entropic cone is really difficult to deal with. So we take the topological closure of that and optimize over this set. But even this is also difficult. So we relax it further to something called polymatroids, which is a set of functions that satisfy three properties: monotonicity, subadditivity, and submodularity. The nice thing about this is that now this is a polyhedral set. So it satisfies a set of linear inequalities, so we can now compute bounds over it. The problem is that the bound over this set, which is a superset of this, is not the same, because we are optimizing over a bigger set, so the two bounds are not the same. So effectively, this is the final slide I would like to show you. It's basically, we know the equality. We know the worst case output size bound is something called the entropic bound, but it's not known to be computable. If we have to relax this because we don't know how to compute this bound, then it'll become something called the polymatroid bound. It is computable, but it's not known to be efficiently computable in a sense that it may be exponential in query complexity. Okay? And it's also not tight. It is only tight in several special cases, including the case of the AGM bound, for example, if you have heard of the AGM bound. And the other kind of interesting thing is that if you relax this even further to subadditive functions, and you will get something called the integral edge cover number under cardinality constraints. So this kind of gives a very clear explanation of where the integral thing comes from and where the fractional edge cover numbers come from. It's basically coming from a hierarchy of relaxation of entropic functions. Okay? And lastly, this is basically the landscape of problems and solutions. So as you push the constraints from simple to complex, by simple I mean cardinality constraint only, then the bounds are really nice and computable, and then the argument is typically based on the holder argument, and there are several worst-case optimal join algorithms that match this bound. They have nice properties. When the constraints become more complex, then the bounds are either tight but not computable, or not tight but computable. Okay? So there are things in this realm is very difficult to handle. The only known algorithm is Panda, which has hidden factors I don't want to tell Moshe about. So, but in the write-up, I have presented an algorithm which is kind of somewhere in between simple and complex. It's closer to the simple side, and it has some of the nicer properties, but it's not just cardinality constraints. So, thank you. I try my best to avoid his questions.
Actually, I was not going to ask you about the constants, but following Mike Benedict approach, ask you about how do these algorithms perform in practice?
Yes, so that is sort of a loaded question. So the honest question to that is that it depends on the workload. So I certainly can show you real workload for which these algorithms will beat any other typical join algorithms. But there are also other workloads that have been optimized by the community over 50 years, certainly that will beat at least our implementation of this algorithm. But they will never beat us by like a huge factor, because our algorithms are worst case optimal. So we never go like way too bad, right? But we don't have things like hash join, or we don't implement some of the wisdoms that have been.
But the other, if you go again to cost-based optimization, it's just finding a good query plan by itself is a hard problem, and a lot of literature of the past 20 years about trying to still how search the space. And the magic here seems to me there's almost no search, right? You basically start from the degree constraints, and you derive a plan from that effect.
That's right.
And there is a complexity of doing query planning, which you have not explicitly addressed, but it seems you have a huge gain in query planning complexity compared to cost-based optimization. And so it will be really interesting to look at, one is how much time are you spending on coming up with a query plan, and then comparing the performance of the results of the cost-based optimization.
Yeah, that's a great question. That was actually under work at LogicBox for a while. We do have a cost-based query plan based on these algorithms. So that was like one of the open problems that I put in the write-up. We don't have like the depth of the theory for the cost-based plans compared to this theory. So that's very much is open. Yeah.
So if I'm here, my other question is that with their previous talk that have to do with various 3D compositions, and the answers of all these other approaches to do this variable elimination, right? What we could used to call early projection. Right. Nothing of this shows up here, right? We're not doing any early projection. So I'm curious, where do you?
Oh yes, we do that, but I skipped that that part as one of the topics that I don't have time to cover. There we go.
Yeah.
Yeah. So basically, the top level plan is actually to use 3D compositions or variable elimination, and then we have to solve the subproblems. And in the subproblems, we have to use these two. Yeah.
Okay. Thank you.
Thank you.